So I will be talking about how we can leverage CCS inside Kokkos. I'm one of the performance engineering team lead at the RCF, and I do auto-tuning frameworks on my free time. So the first thing I want to talk about today is online auto-tuning, because auto-tuning is usually some kind of big orchestrator that is running your full app and exploring a design space. But I think it's a very narrow view of what auto-tuning can be. And so I don't really like this workflow, and I think it leaves a lot of performance on the table, and it incurs a lot of overhead. So especially the context-specific nature of auto-tuning regions based on the particular problem your application is solving, or on the particular schedule, on this particular architecture of the different kernels, which will make the environment different, is one of the issues that leaves performance here. And also it's very expensive because you run the full application just for the purpose of optimizing it. So one of the potential solutions, and Vivek presented earlier his talk about the Kokkos tool and the auto-tuning, is to do online auto-tuning inside our runtimes, our application, our JITs, and so on, to explore the design space as the application is running and converge towards a more efficient application. It means that you can also split the problem. The different regions of the program are tuned independently from one another, rather than convolving the whole space inside a giant search space. And of course, since it's done at the runtime level, well, maybe application writers don't really need to worry about it in most cases. So what is the problem in order to implement this online auto-tuning? Well, it requires a paradigm shift from the tuner community. So tuner frameworks, as I said previously, will need to transform from orchestrators into service providers. And the performance of the tuning process itself will become critical because the smaller the region you want to tune, the bigger the overhead could be if the cost stays constant. And the last thing is portability is an issue. So you need to plug your framework in a broad range of application, runtime, and JITs. And that may be difficult if your framework is written in Python. So the idea, and that's something, a pet peeve of mine that I've been advocating for a very long time, and when ACP gave me an opportunity, I started working with the Kokkos team on co-designing this, is we should provide a low-level interface to describe those tuning problems and to describe those tuners so that we can plug different tuners into different runtimes. And Kokkos is one example of such a runtime. All right, so the library I will be talking about today is called CCS. It stands for Seed Configuration Space. Its objective is to be a portability interface for online tuning. We should be able to describe in a low-level API parameters, configuration space, tuners with an ask and tell interface so that you can ask for configuration, try it, and then give back the result to the tuner. We need to support the usual nice features of tuning frameworks and modern tuning frameworks, constraints, statistical sampling stuff, how to manage the distributions. And the idea is really to bridge auto-tuning frameworks and our applications and runtime. And of course, we wanted to demonstrate those capabilities. We have a little bit of constraints we want to apply to the project. We want to be performant. We want to be easy to bind in higher level languages so that we can prototype tuners in those higher level languages. We want to be able to leverage those high level languages tuners from C and C++. we needed to support Kokkos Tools since we were co-designing with Kokkos. And at first we saw it as a drop-in replacement for a package, Python package which is called config space. But we evolved in something which is way broader than what they provide nowadays. So the ancestry is a bit lost. So we chose to design a C API with reference counting to ease memory management. Most of the objects are immutable, so you don't need to synchronize, and you don't really need to worry about memory. We limit memory allocation to what is strictly necessary for the library, meaning you need to manage quite a bit of buffers in order to communicate data to the library. So we are not hiding those allocations so you can optimize them. We decouple the statistical aspects from the problem description, so that's quite important if you're in the tuner side of things, much less from the application, most probably. And we try to be as flexible as possible if we don't harm performance. So what is the status of the library? And I won't go very much deeper into the details. CCS is, well, I say nearing the first release, but we've been doing that for 5 years, so almost. So it's ongoing, but it's pretty mature. So we support numerical, discrete, ordinal, categorical parameters, string as well, but I won't have time to explain, but it's for Kokkos specifically. We have random generators which are based on the GSL. It's the only dependency of CCS, the GNU scientific library. We don't depend on anything else. So it's pure C. We support several distribution that allows you to mix distribution together, so multivariate and mixtures, and the usual uniform, normal roulettes that allow you to describe your sampling space. We have configuration spaces with constraints, so it does not really apply to Kokkos, the constraint side of things, but it is very important for other kind of problems I will be showing briefly. We have expressions to describe these constraints, of course, and the objectives we want to optimize. We have feature space, which are a context where configuration space and objective space are defined. This is something that was added by the co-design work with Kokkos. And that is something I would have missed if Kokkos was not there. So we have, of course, binding on those different spaces, meaning configuration from a configuration space and evaluation from an objective space, features from a feature space. And we have tuners with ask and tell interface to optimize configuration spaces on objective spaces. All of these are serializable, deserializable, so you can start building more intricate schemes than just shared memory tuners. So you could have a client servers, and I have demonstrators of that. And we have Python and Ruby bindings as example with tuners, and then you can call these tuners from a C application. And I have those demonstrators as well in the sources. So it's integrated in YTOP in deep hyper-tools. The state of the integration kind of depends on who is maintaining deep hyper, especially. And we have in the CCS repository a Kokkos connector that we can use to auto-tune Kokkos region. And I will show a bit how it works. All right, so this is just an example of how the library can be used from a Python perspective. So this is a real example that Mary Hall and her students from the Proteus Tune team at ECP worked on. So it's an OpenMP optimization problem described with mostly categorical and ordinal parameters, but we have a set of constraints, conditions, and forbidden clauses that are used when we create the configuration space. And we have a grammar that we define that allows to describe these conditions as strings, and we are passing them and transforming them. And then you can sample this space, and that gives you an idea of the kind of way you should be able to use the library from the high level. So if you were to build a tuner on top of that, you would sample the space and then return some of the sampled configuration to Kokkos to try, and then Kokkos would give you back the results. But I'm not going to have time to go through a lot of code examples, but it was just really to give you a feel of the kind of integration from a C library with a nicely written binding you can get. All right, so how do we tune Kokkos region with CCS? So the Kokkos tuning model it's very nice, Vivek. Thank you very much for presenting everything this morning. So I don't really need to spend too much time on it. So the tuning models, there are two in the Kokkos Tools. There is an automatic tuning model where Kokkos maps regions to its construct. So, for example, Kokkos parallel 4 will be a region you will be entering, and it could have tunable parameters. So they could be tiling, they could be policies. And there is also context parameters that Kokkos will define automatically, like, oh, what kind of kernel are we running, what is the name of this kernel, and so on. But you also have user-defined tuning model, where the user uses a small DSL inside Kokkos to declare tuning parameters and context parameters, and define their region boundary by saying, okay, we are entering a context, we are leaving a context, or we are querying for some of values from the tuning interface. So you have those two modes, and I think users will be pretty happy using the user part of it. But the automatic part is free for everybody. It comes with Kokkos. So this whole API, tuning API, it's event-driven. So the idea is that Kokkos will emit some events. For the tuning perspective, it's irrelevant whether it comes from the automatic Kokkos layer or if it comes from the user. So the idea is Kokkos will declare an input type, which is a context variable. It has a name and it has a type, which is unique associated to this name. And it can declare a second one, for instance. And then it will declare an output type, meaning a tunable variable that it will query for value later down the road. Then it could declare another input type. So the order is not very strict. And then it will say, oh, I'm entering a region, a context, a tuning context. It begins here. And then it will set the context values for this, and it will request the output values, meaning the tuning values that the tuner should provide. It could be nested with another context here. That's what I'm showing. And inside the context, since it's the first time you're encountering, you're declaring a new output type. So the order is pretty flexible, and you need to be careful about the assumption you make about what the runtime would be doing. Then, before requesting output values, it will set this new context variables, if they exist, and then request output values for the inner context. And then it will execute something. At the level of the tuning library, this is at the end of the request output values, you would be taking a timestamp, for instance, if you want to optimize for time. And when you reach a context end, you will take a second timestamp, and what's in between would be the measurements you would be getting. And then, during the context end, you will send back, you will inform the tuner that is running that the configuration that is returned to Kokkos through the request output values gave this kind of performance. And then the second context will end, and you will do the same thing. The first context will end, and you will do the same thing for the first context tuner. So here you have two independent tuners running, potentially, one for the first context and one for the second context, with their own tuning values and their own context variables. So let's talk briefly about the CCS Kokkos connector. So we co-designed it with Kokkos Tools and David Polyakov in particular. So you can find the source here. We map tuning events to the Kokkos Tools callback, of course. This is done by Kokkos, and we inside the connector, so we define those callbacks, and inside the connector, we map the context variable to parameters and feature space, and tuning to parameters. Context variables go into feature space, tuning variables go into configuration space. Those define a tuner. I'm not talking about objective space because for now it's pretty not supported in Kokkos. And then we return configuration when we request output values, and we send back evaluation to the tuner at the context end. So the tuner, the connector is a proof of concept, meaning it's only implementing a random tuner. You can use compile option to debug and profile what's happening, but the idea is a baseline, because random tuning is a baseline you should always compare yourself to. So there are a set of benchmarks which are in the Kokkos tuning playground. The link to the Kokkos tuning playground is in the link I gave above. And inside the link it says you should use a fork of the Kokkos tuning playground, and I advise you to, because I had a number of bug fixes that have not been merged, but these are required if you want those examples to work. So here we have the toolbar example of the Kokkos tuning playground. There are several others. This one is a very horrible stuff from a tuning perspective, because you have two context variables, W and X, that can be 0 or 11. It's random. And what the tuner should answer is two variables that are exactly W and X. But it's difficult to learn this. And especially for a random tuner, since you're testing randomly, you will miss most of the time. And the penalty you pay is a difference to the correct guess in microseconds, or 10 times this. So the benchmarks by itself runs in 11 seconds, because there is 100,000 configuration tested. And so it's designed to run in 11 seconds. And by using the random tuner and a budget of 500 evaluation, we can bring this down to less than half of the time. So you have less than 5 seconds runtime while you use the tuner. And using the tuner is just adding the Kokkos Tools libs environment variable and pointing it to the CCS Kokkos connector library. So this is as simple as that to get a speed up on this benchmark. All right, conclusion, it works. The API from Kokkos allows you, and the context allows you to describe what's required to build a configuration space and have a tuner work on it. We get performance improvements using a baseline random tuner, meaning if you want to deploy a tuner that is smarter than the random one, you need to build it. And that may not always be super easy. And so we have a low-level API which implements portable auto-tuning as a service. You can easily prototype stuff in high-level language. We have the examples in the source code of invoking a Python tuner based on the CCS API from a C application. So we don't have any excuse not to plug those inside and play with them. And the perspective of the work is embedding auto-tuning everywhere, in runtimes, in compilers, in JITs. because there are lots of opportunities for tuning we are not taking advantage of right now. And we should continue the co-design effort with the Kokkos team, and be happy working with that. And one of the next goals would be to port real tuners to CCS, or design new tuners in CCS so we can use them in Kokkos and other libraries. Questions?
Any questions? Yeah, so you sort of made this argument, which I sort of somewhat buy, that you should move from this sort of orchestrator model to a service model. Do you think those are actually mutually exclusive, or that if you have an orchestrator, it should also be providing some API? You know, like, can these two ideas mesh?
So you can definitely use the API on an orchestrator model. That's what we do in YT-opt, which is not an online model yet, or partially an online model because we used it in some workflow as an online tuner, but it's also an orchestrator model. So the abstraction and the library by itself doesn't mean you can't use it in both contexts, and I don't see orchestrator model disappearing. So yeah, I was a bit provocative. But
Just to comment on that, yeah, so I guess there's also the distributed auto-tuning, so with MPI awareness, auto-tuning, I think that would also be beneficial, right? The orchestrator model.
It's interesting because, as I was telling, serialization is supported, so you can do a client-server tuner with that. So you could have a Kokkos MPI application with a different region asking to the same tuner for configuration and sending them back. So you could gain distributed insights while you run your applications by creating distributed tuners. So there is an advantage to doing online, even in a distributed manner, to gather knowledge more efficiently and then redistribute it through the different ranks, assuming they are running the same kind of kernels, which is usually the case. But I agree that an orchestrator on an MPI application is a proven model. I'm not going to argue you're not getting gains here. I'm saying we can maybe gain faster and more adapted to each runtime, because if you're doing an orchestrated model, you have a test case you're optimizing for. If you're running the application, it will be running tomorrow. To optimize it, it's too late. You need to be able to run the application that you have not run already, and I don't think you can do that with the orchestrated model, unless you've already tried all the parameters, and in this case, you don't really need to run it again. So yes, the orchestrator model only applies as long as you can generalize the results you've got on your synthetic benchmarks that you use to tune it. Online tuning can give you benefits for any configuration.
All right, thanks, Brice.